Okay, I'm going to pick up where we left off last time and talk a little bit more about the nucleus of the atom and this concept called binding energy and mass defect. So before we introduce that, let me just remind you of what we talked about last time. We talked about how the nuclei were measured experimentally, and it was determined that they all had the same density, that adding more particles didn't make it kind of collapse or crush into something that was more dense at the middle. And the reason for this, the reason why atomic nuclei have a constant density, has to do with the nature of the force that holds the nucleons together. We haven't said very much about this force yet. I believe we've named it, but beyond that, haven't said much. So let's talk a little bit about the strong nuclear force. And I'm sure it'll come a big shock to you that it is a very strong force. It is the strongest of all of the forces. It has the largest magnitude. It overcomes certainly electrostatic repulsion. Otherwise, atomic nuclei could not exist. A bunch of positively charged objects would not stick together without a force that was stronger than that. However, and this is where the constant density comes into play, it has an incredibly short range that essentially falls to zero at very short distances, okay, even though it's very strong at very close distances. So what that means practically is that as you add more and more protons to an atom, they don't all affect each other. This proton is really only affected by the nearest nucleons. And once you start getting even beyond that, then it has very minimal effect from these nucleons here. On the other hand, the electrostatic repulsion force from the faraway protons is still very much actively working on this. So one of the effects of this is that the density stays constant. It doesn't crush down into a smaller object, but also as the nuclei start to get really big, then the strong nuclear force, as strong as it is, isn't able to hold it together anymore. Really adding more protons doesn't do anything to hold the protons on the other side because the force falls off over such distances. So we could say as a result, atoms will start to crumble, to use the technical term, when the nuclei get too big or fall apart, far apart from one another. And this is where radioactivity will come in, and we'll talk about that more next time. All right. Let's introduce the idea of binding energy then. So binding energy, sometimes symbolized Be, is defined to be a measure of the amount of work. Remember, work is just energy, giving energy to something. The amount of work it would take to disassemble a nucleus. How much work do you have to do to pull it apart and remove all those protons and neutrons, basically break the strong force and pull them apart from each other? It's going to take some work. It's going to take some energy to make that happen. And when we find, okay, here's where we're going to bring in, for the first time, Einstein's famous equation, E equals mc squared, that when you give energy to something, which is what you have to do to pull nucleons apart, you've got to do positive work and you've got to give it some energy. That because of energy mass equivalence, as you give energy to anything, its mass increases. There's all kinds of examples of this. Even if you heat a cup of coffee in the microwave and make it hotter, it's actually slightly more massive, which means it has more gravity. It weighs a little bit more when hot, and it also has more inertia when hot than it did when it was cold. Usually this effect is pretty negligible for something like a cup of coffee. You wouldn't necessarily notice that because whatever energy you add to the coffee has to get divided by the speed of light squared, which is an absolutely huge number, so the mass increase is pretty minimal. But when you take apart a nucleon, or nucleons from one another, a nucleus, we start to notice this effect more and more, and that this increase in mass that comes from doing work to a nucleus is sometimes called the mass defect. What's the difference in mass before and after you took it apart? That's equal to the energy or the work that was required to disassemble it. Also useful reference here, the speed of light, if you remember from before, is 3 × 10⁸ meters per second. So I could use that to make calculations between mass and energy. And practically speaking, mass is the energy divided by the speed of light squared. So this is separate from that. So we'll draw a line there. The units, so the dimensions that we have then for mass energy, because really it's one thing, mass energy, they're equivalent to each other. We said already that there's the atomic mass unit, which is about the mass of a nucleon, and that's in kilograms, 1.661 times 10 to the negative 27 kilograms. But we could also write that in terms of energy per speed of light squared. And this comes out to be, when measured, 931.5 mega electron volts per c squared. So now we can make a connection between energy and mass when it comes to taking apart a nucleus. And we'll see some examples of why that matters or how that works here in this topic, but certainly in some future topics as well when we get into radiation. Okay. So, okay, let's kind of look at practically what this means. Okay. The binding energy then can be determined by figuring out how much the mass changes when the particle is taken apart, when the nucleus is taken apart. So the binding energy is the mass of the individual parts when it's disassembled minus the mass of the starting atom. So look at how much the mass changes. You can figure out how much work you had to do to pull it apart or disassemble it. So here's a particular atom, for example. It has 3 protons. So of course, it's our good friend lithium. So we have lithium. We use our atomic notation, 3 protons. And it looks like it has 5, 1, 2, 3, 4, 5, yes, neutrons. So it has 8 total nucleons. So this is lithium 8. And I also have some electrons here, since generally lithium nuclei have electrons, so it's electrically neutral. And then if I were to disassemble this, not entirely, I'm going to leave the electrons alone. I'm just looking at the energy in the nucleus. Disassemble the nucleus. I would have 5 neutrons, and I would have 3, not protons, but 3 hydrogen atoms, since they're both paired with electrons. Okay. So upon disassembling the nucleus, I have 3 hydrogen atoms, 5 neutrons, and a partridge in a pear tree. So if I look up the masses of these things, the mass of 3 hydrogen atoms is precisely 1.00783 atomic mass units. That's the mass of each one. Okay, just a little bit over 1. And I've got 3 of them, so I got to multiply that by 3. And the mass of a neutron, 1.008665, so slightly more massive than a hydrogen atom, atomic mass units. And when I look up the mass of lithium-8, it has a mass of 8.022485 atomic mass units. Okay. So if I want to calculate the binding energy, how much work had to be done to pull this thing apart, I need to take the mass that I end with and subtract the mass that I started with. So let's do that here. So the binding energy at the end, my final binding energy, is I've got 3 hydrogen atoms, so 3 times the mass of 1 hydrogen atom, plus 5 neutrons, and that's the mass that I end with. And then I'm going to subtract the starting mass of the whole nucleus. So it's pretty simple math here to figure out how much the mass has changed by. Now it's going to be almost the same, but not exactly the same. So when we calculate the mass defect, this number, the mass of all the parts, in case you're curious, comes out to be 8.066815 atomic mass units when I have them all as individual parts. But when they're together as a lithium atom, it's 8.022485. So we'll see that the lithium atom has less mass than the parts that make it up, because we had to do work to pull them apart that actually increased the mass of the objects. So how much mass, how much work did we have to do? The difference between the 2 masses, it's pretty small, but it's not totally insignificant, 0.04433 atomic mass units. And I could make a unit conversion using the conversion I showed you on the previous page, that there's 931.5 mega electron volts available for every atomic mass unit. So the amount of energy, the amount of work that had to be done to pull this thing apart is 41.29 mega electron volts, which if we consider the atomic orbital levels we studied in the last unit was the electrons transition. We were talking about electron volts. Now we're dealing with millions of electron volts instead of just electron volts. So very large amount of work done to pull this thing apart. So what we'll finish with here, we have a graph that we'll see more and more of as we go forward, that we consider the different elements and we look at how difficult their nuclei are to pull apart. We can make a plot of the binding energy per nucleon as a way of comparing one nucleus to the other. So this isn't the total binding energy of the atom. Obviously, the really big nucleons will take a lot of work to pull them apart, but this is the binding energy for each nucleon. Basically, how much energy would it take to take one nucleon out? How much work to remove one proton or to remove one neutron from the nucleus? So it's the total binding energy divided by the number of nucleons. So on the horizontal axis, we have the atomic number. And so as we add, the total number of nucleons, the atomic number would be Z. So the total number of nucleons, as we add more and more, we're getting our larger and larger atoms. And if we have no nucleons, then obviously no work is required to pull them apart. Okay. And as we add additional nucleons, as we start going up, then it takes some energy to remove them. And we find that if we have two nucleons and we try to pull them apart, it takes a lot of work to pull them apart, but three are a little less stable. So it's actually a little bit easier to remove one from an arrangement of three. And then as we start going up to 4, 5, 6, 7, 8, 9, 10, we start getting a relationship like this where the binding energy becomes more and more. But then interestingly, it reaches a tipping point and then it starts to go down. It kind of tails off a little bit like this. So if we were to plot the whole chart, it'll look something kind of like so, or to draw a smooth curve through all of this, the binding energy per nucleon curve. And again, what the binding energy per nucleon curve is showing me is it's saying how hard to pull out one nucleon. It's a measure of how difficult it is to remove one. How much work is required to pull in one nucleon out of the nucleus. And what we find is essentially what happens is that the difficulty of removing a nucleon gets bigger and bigger. So these are actually the more stable atoms, very difficult to pull apart until it reaches a peak. Call this the tipping point. And then at some point past that, it starts getting easier to remove nucleons and the atoms become less stable. So more nuclei become more stable, but only up to a point. And there are a number of atoms that this could be because it's just a nucleon number. So it could be different isotopes of different elements. But one example of something that's maybe at this peak would be iron. Could write iron, Fe. Iron 56 is at the peak. Very stable, very difficult. And in fact, this is the heaviest element you'll find in stars like the sun. As atoms fuse together into lower energy states, we'll talk about fusion later as well, then they create heavier and heavier elements only up to a point, because then after that, you don't get energy out by fusing atoms together anymore. So we'll look at nuclear fission, which happens here, where these things tend to become unstable and to crumble, and these things tend to want to stick together. Much more to say about that in future activities. So if we look at what it is that I'm going to give you to work with here, formulas and constants, you don't have to memorize any of these constants. So knowing charge, knowing masses of things like electrons, protons, neutrons, also the conversion from atomic mass units to kilograms or mega electron volts. We talked about the Fermi radius, which could be used to determine the radius of any nucleus. And then here we've got E equals mc squared. So let's take a quick look at a couple of examples here before you jump into the activity. So here we have some data, and again, you don't have to memorize these numbers. These would be given to you. We have the nuclear mass of helium-3. We have the mass of a proton and the mass of a neutron. In this case, we just are given the nuclear masses. If I gave you the atomic mass of helium, which would count the electrons as well, then you would need to use hydrogen atoms here to account for those electrons. But in this case, there are no electrons mentioned. We just have the nucleus. And so when it's disassembled, we just have protons and neutrons. Okay. So use the above data to deduce that the binding energy per nucleon is 2.2 mega electron volts. So again, this is another binding energy calculation. And what I'm going to do is just look at the parts afterward minus the mass that we started. It's just a difference between those. So let's see, this has 2 protons. So when it's pulled apart, we'll have the 2 protons. And neutron-wise, if we have 3 total nucleons, there must be just 1 neutron. 0.00867. So this is once it's disassembled. This is the mass of everything. And then we'll just subtract the mass of the starting nucleus, 0.01603, to figure out the mass defect. And the mass defect, 0.0072 atomic mass units. Has slightly more mass after disassembled than when originally together. And so that work done to give it that extra mass is a certain amount of energy that had to be input. So we can multiply that by 931.5 mega electron volts to get the binding energy, total binding energy of the nucleus, 6.7 mega electron volts. But the question didn't ask me. It says to deduce that it's 2.2. That seems like I made a mistake here. But it asked me to find the binding energy per nucleon. So basically, how hard is it to remove 1 nucleon? So I have to take into account that this nucleus has 3 total nucleons. So we'll do the 6.7 mega electron volts divided by 3 nucleons. And that's where we get the 2.2 mega electron volts per nucleon. How much work to pull one of them out of the helium nucleus. All right, we'll take a look at the final one here. Solve for the approximate diameter and density of the helium-3 nucleus. So to find diameter, I need to know its size. So here we can use our radius equation, the Fermi radius equation. So, where's my formula here? Okay. I've organized myself. I have these memorized. So the Fermi radius of a nucleus is equal to the Fermi radius times a to the 1/3 power. So in this case, my Fermi radius is 1.2 times 10 to the negative 15 meters. A is the total number of nucleons, which in this case is 3. So I have the cubed root of 3. And we can find this value. So this will give me the radius of the nucleus, and it asks me to find the diameter. So the diameter is going to be twice that. So I double this number, we'll get the diameter. So we'll check that on my calculator here. This comes out to be 3.5 times 10 to the negative 15 meters. How far apart one side of the nucleus is from the other. And the last question is a question of density. Density is mass over volume. And I can take the total mass of this nucleus, which I was given 3.016 0.03 atomic mass units and convert this into kilograms using my unit conversion from the previous page. Yeah, that's 1.661 times 10 to the negative 27th. Kilograms per atomic mass unit. So we have the kilograms of mass of one nucleus divided by the volume, and since it's a sphere, 4/3 pi r cubed, where the radius is half the diameter. So if I plug all of this into my calculator, let's see what I get. So these are really tiny numbers, but when we go to find the density, we find that the nuclei are incredibly dense. I get 2.3 times 10 to the 17th kilograms per cubic meter. So will this float in water? Well, that's kind of a funny question. Yeah, probably, since it's just a single atom. But if we had a large material, certainly not. So I hope that's helpful. You can jump right into the activity now. Have a good time.